Hello, good evening, morning, or afternoon, whenever you tend to watch this. This is Mr. Zod again with the chemistry classes. So, uh, just to bring us up to speed with what we covered today, uh, this is November 9th, Monday, or the lesson from Friday, depending on which period you're at. Um, Today, we're just going to go over the first half of assignment number 8 and a little recap for assignment 7 and, well, some announcements. So I said that in reverse order. So we'll start with the announcements first. Um, as you may know, on Wednesday, we have Veterans Day. That is a holiday. You are not showing up for class. And we're going to make up for that odd day on Friday. Friday is a regular odd day. Also on Friday, our 15-week report card is due. So I finalized those grades. In fact, let me just go ahead and show you the agenda for the week. I finalized the grades for the 15-week report card this weekend. If you have any last minute work you want to turn in, feel free to do that by Wednesday if you want it on the 15-week. Otherwise, it'll be on the 20-week, which is your last one, and also coming up real soon. Um, I think that's going to do it for the announcements. No, we have one more. On Friday, assignment 7 will be due to be turned in, and it's a little minor one. So you got basically 3 questions to answer. We did most of it in class, so uh, you have that to turn in on Friday. This week we'll be talking about assignment number 8. That's kinetic molecular theory. That's what KMT stands for. And on Friday or Thursday, we'll try to finish off that assignment and get started on some notes for thermal energy, phase changes, and temperature. That's a maybe, though, because I don't know how long assignment 8 might take. So X that out. And let's take a look here. Nothing really changed. We just added assignment 8, added the notes. So let's go ahead and make sure assignment 8 is copied and pasted into our evidence notebook. So highlight the entire thing. It's about 2 pages long. It's 8 questions. And copy and paste that into the notebook. I've already done it on my end. You see here, it's the last thing. And so I said beforehand, I'm going to do a little review of assignment 7 first. And so for assignment 7, we're talking about the properties of gases. And before that even started, we're talking about heat. That's what this entire unit is about. We're talking about heat and how it interacts with different variables like pressure, temperature, volume. And we're basically getting into how gases interact. Traditionally, this would normally be the section where we start talking about the gas laws and the ideal gas law, but that's taking a back seat this time around. And so for assignment 7, we're looking at those properties of gases. The first question is one for you to answer. How does a marshmallow react if you put it into a syringe, you put your thumb on the tip, and you pull on the plunger? How does the marshmallow react? Because that's a investigation into, pressure and volume. All right. For the rest of this, the analysis part, we're looking at this PhET simulation and we're trying to build relationships between these different variables, pressure, volume, and temperature. Each time around, we hold something constant. That means that variable does not change. So when we hold temperature constant, we're moving around pressure and volume. If we hold pressure constant, we're moving around temperature and volume. If we move volume constant, we're moving around temperature and pressure. And so make sure you have your graphs, you're able to edit them in, right? Draw that line, show the relationship, and basically that's what you're up to. Conclusions are, what do you think is going to happen to the volume if the pressure increases, but so does the temperature? And then to summarize those parts, here's what I'm going to have and just delete right now. If pressure and volume are the inverse, then the relationship is if one of them is increasing, the other will typically decrease, and vice versa. So you do that part on your own, though. Now, we are back to assignment number 8, kinetic molecular theory. And just to make this clear, this is a very important part of chemistry. The idea that molecules have energy, that's what we're talking about. Kinetic, kinetic energy, molecules. The idea that molecules have energy is such a huge part of our, I guess, course. It really can't be understated how important that idea is because it leads into so much. So, aligned with learning target number 5, that has to do with systems, and this is due before Thanksgiving break, right? Where you're ending off the break. We're starting off the break with ending this assignment. Now, as always, we do part of this in class, so part of it will be on you as well. Now, the vocab words are normally something I would let you figure out on your own. This time around, those 2 words that we're referencing here, vocab words number 3 and 4, the book does an adequate job at explaining them, but it is just that. It is just adequate. And so I'm trying to make it more relevant. In your book, the definition for molar mass is defined as the mass of 1 mole of a substance, which again is accurate. But to make it more relevant to chemistry, we want to talk about the mass of an element. And so when we go to a periodic table, here's one pulled up, every single element has a pattern, right? We've got a small number at the top, we got a symbol for the element, and we have a large number on the bottom. The small number up top, that's the atomic number, right? It goes in order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 42, all the way up to 118. That's a small number, right? The much bigger number at the bottom is what we call the atomic mass or the atomic weight. More importantly, though, 1 mole of this stuff actually weighs 95.95, weighs 112.41. And so if I took a mole of calcium, I know a mole of calcium weighs about 40.078 grams. And so this concept lets us do actual reactions with it, right? If a reaction is a chemical recipe, then the mole lets you, fill out that recipe. It lets us know we need 8 grams of oxygen because we only need half a mole in our recipe. So we only need half the amount of oxygen, so not 16, but 8. And so that's what we're rolling with here. X that out. And so sodium, for example, has a molar mass of 22.99 grams per mole. And so molar mass is measured in grams, and we're measuring moles, so grams per mole is what we're seeing here. And again, in your book describes kinetic molecular theory as a model, and that's the only relevant part in your book. The rest is what we're going to deal with here. A model lets you predict functions. It lets you predict and examine how things work in real life. And so a model for kinetic molecular theory is it lets you know that molecules have kinetic energy. That kinetic energy creates a force. We established earlier that forces in a specific area create pressure. And if you put a pressure inside of a container, now you fill out that volume, right? And so it's like a domino. You set one up, and now all these ideas come from that one idea, and that's why kinetic molecular theory is so important. It lets us predict so much more. And we'll get practice with this later on. And so in a balloon, right? If you blow air into a balloon, you have blown particles of air into that balloon. Those particles each have energy. Those particles hit the surface of that balloon and create its volume. And this is just a small example of kinetic molecular theory in action. All right. Next up, we're talking about more balloons, really. As you know, a mole is about 6.02 times 10 to the 23rd of an object, right? It's like a dozen, right? A dozen is 12. A mole is about 6 septillion. So, basically the same thing. But a mole is more relevant for atoms and particles and molecules, because if we start talking about things like coffee, you would have literal oceans of coffee if you had a mole of it. If you had a mole of donuts, you'd have a mile-long or mile-thick layer of donuts across the surface of the Earth. A mole is really only relevant for particles and small things. Now, moles and most gases and elements are measured at something we call STP. STP stands for standard temperature and pressure. Standard temperature is freezing, 32 degrees Fahrenheit, 0 degrees Celsius, or 273.15 Kelvin. Pressure, standard pressure is just the pressure that most of you exist at right now, which is 1 atmosphere. It's sea level pressure. If you live in like Asuncion, Paraguay, I think is the capital, you're living at above sea level, and so the chemistry is different there, built different. Now, the fun thing is about STP, any gas, any gas at STP, standard temperature and pressure, will occupy the same amount of space, 22.4 liters. And so in this image I ripped from your book, we got small hydrogen gas, right? That's a very tiny thing. We got larger oxygen gas, a little bit bigger, and we got even larger still, carbon dioxide. Now, these are all differently massed, right? One is very light, one is very heavy, one is kind of at the middle, and yet somehow they all occupy the same amount of space at standard temperature and pressure. And so in the Zoom classes, I had some polls out asking about heavy versus light particles, and let's talk about that. Heavy particles have a lot of mass to them. And so when they hit something, that's a lot of kinetic energy going off at one spot. So the pressure created by the heavier particle is kind of large. Light particles, on the other hand, really don't have that much force behind them. They don't have a lot of mass, so if they hit something, you're not really going to feel it. But they'll hit something repeatedly over and over again, and that's going to create the same amount of pressure that our heavier particle create, right? Think about like one person hitting one spot with a huge amount of force versus another person hitting the same spot over and over again with less amounts of force. The pressure is basically going to be the same. Not basically, it is the same. And so on average, those things even out, and so they create the same volume. Now, we watched 2 videos in class. I'm not going to show the videos because I'm not sure if there's like copyright on them, so we're not going to see them. But for one of them, we have a video of a man pouring shaving cream into a beaker, and then he puts the beaker into a container, and he sucks the air out of that container. The shaving cream expands. And so the idea here is that the pressure, let's go ahead and draw this out. So we have a beaker filled with shaving cream. Here's our shaving cream. Right. So the beaker and inside of it has shaving cream. Shaving cream creates its own pressure, right? There are particles inside the shaving cream. And so that pressure forces the shaving cream to expand outwards, right? At the same time, the air around the beaker, around the shaving cream, forces the shaving cream to stay down, right? And so there is inequality here. They will even out at some point. And so the pressure on the inside and the pressure on the outside are about equal. When the air leaves, when the air pressure in the bell leaves, right? So instead of, let's see if I could undo some of the stuff. When those air particles leave, right, they're sucked out. What happens next is that the pressure holding this thing in disappears. And so these guys are going to expand. And so in the video, you see the volume of this, how you say, shaving cream expand. And so the pressure on the outside decreased. Therefore, the volume increased, right? And so that jives with what we saw in assignment number 7. Let's go ahead and clear off these drawings. In the next video, we have a balloon. You hopefully had balloons before. You fill up a balloon. It's got gas inside of it. It's got pressure holding it in, right? Holding it out. So the shape is created by pressure. And the constant amount of gas, the amount of gas hasn't changed. But if you decrease the temperature of the balloon, in the video, the man puts his balloons into some liquid nitrogen. My dog was here and now she's not. The temperature inside that air decreases. So the air starts to cool down. The particles of that air cool down. And so that means the kinetic energy has decreased. Those particles has lost energy. The liquid nitrogen absorbed the energy, right? So some of that nitrogen went off into space, uh, and now your balloon is left with less energy than it had. The particles that are still in there, right, are going to collide with each other less often now because, right, beforehand they were very energetic, bouncing off the walls, hitting everything. And let's go ahead and draw this out as well. So we have our balloon. Inside that balloon, we have our particles. And so they'll collide, right, however which way, and then maybe they'll bounce off something else, maybe they won't. It's very energetic in there. If you cool it down, though, if you cool off the balloon, those particles don't hit each other as frequently because they're slower. So they'll be way slower. And so you're not going to really see the collisions happen as frequently as they used to. You'll notice also that I drew this one a lot smaller than the other one, and it's because of the same thing. These particles hit the sides of the balloon less frequently, which means that the air pressure is actually crushing this balloon more so than it was beforehand. And so particles collide with each other less often, and that decreases the volume of the balloon, which again, from assignment 7, go ahead and clear these drawings. From assignment 7, if the temperature went down, we could also expect the volume to go down. It's interconnected. And the last one was a picture of a soda can I stole from Google. Thank you, Google. It's just a picture of some soda that was left inside of a hot car. Now, it looks like someone took a can opener to it, and I'll say you right now that the way these things are manufactured, it's one roll of aluminum and then a cap, because this part, the top, typically requires more machining, right? It's got a tab on it, so you could open it. It's got like the little switch thing. So it's a little bit more over-engineered, so they have to kind of like clamp it on and then pressurize it to attach. So the question being asked is, why did this thing open? And the answers from multiple classes was the temperature, right? You heat up the energy inside that gas through the sun and the carbon dioxide, right? You pressurize it, and then that raises the pressure, and all that pressure has to go somewhere. And if it can't, well, your can's going to explode. And that pretty much wraps up to what we did today in class the ninth. And so next time around, by Friday, I'll post up another video going through 6 through 8, as well as the notes if we get to it. So if you have any questions, comments, or concerns, please feel free to leave me a message on Schoology or send me a message on my email. You guys should have access to all of that. So hopefully this video has been good, and I'll see you all in class later. Bye-bye.